by Excel AI. Just some background information. Excel AI is a 501c3 nonprofit organization, and our mission is to lower the barriers to entry in engineering artificial intelligence while fostering inclusion. So specifically, we like to focus on underrepresented groups in tech and helping people that potentially will be displaced by automation and job loss due to automation. So really helping people that are really new to the industry get started in AI engineering. So we're really glad to have you here today, and the way these sessions run is we really try to cover all the basics in machine learning and deep learning, what software packages you need to use to get started, what the basic concepts are, and then from there give you some hands-on experience working with a few applications, and hopefully to get you really interested in introduction to machine learning. Give them a round of applause, please.
Hello, good morning everyone. So this is Introduction to Machine Learning. If you're here for advanced, super advanced AI talk, that is not this. This is the beginning of AI. This is where AI begins, the very first step. So yeah, we're doing Introduction to Machine Learning. I'm going to introduce myself. I currently work as a data science associate for Open Data Science Conference. Has anyone here ever been to ODSC before? Got a couple of hands. So they're the world's largest data science and AI conference. They have a conference coming up in San Jose in about a couple of weeks. You should check it out. And we have a conference in Boston and London, and this some of the best talent in AI and big data shows every year. So that's my day job. I have a night job, and that is a data science instructor for General Assembly's part-time data science course. It's a 12-week, 6-hour-a-week course where we cover a bunch of introductory data science topics such as visualization, machine learning, NLP, and more. Okay. So let's go to the presentation. So there's two parts to this presentation. There's the actual presentation, the slideshow. I'll go over what is machine learning. I'll go over supervised versus unsupervised, sort of the two main types of machine learning. And then in the second half, what we're going to do is scikit-learn demo, where we build our own machine learning model. And we're going to train it using Spotify data, okay? And we're going to cover some topics such as training test splits, cross-validation, and model evaluation, okay? Now before we get into the presentation, a very important, very hard question to ask. And that is, I need a brave volunteer. What is being depicted in those 4 images? That's a serious question. House, yes, okay. I'm going somewhere with this. It's not just a total joke here. Okay, so the question is not, the main question is not what are those images. The main question is, how do you know the thing depicted in those 4 images are a house? Now think about that. Really think about that. How do you know that those things are a house or houses? What? Train on what? Yeah, but how did you know it's a house? How do you know to call that a house? But there was, think about a time in your life where you did not know what a house was. Someone told you, your parents probably, or a preschool teacher, told you, look at this thing here, that's a house. So you learn from labeled data, basically. You notice this, your 2-year-old, 3-year-old mind, whatever age you were when you first learned what a house was. You saw images like these, you see, okay, they're kind of big, they have these pointy shapes, they have these sort of styles, and then your parents told you, hey, look, that's a house. So that's sort of how machine learning works. We are training a machine to learn from labeled data. And the machine notices that this type of, this data right here has this sort of characteristics, and that's why it's labeled class, this certain class. But we notice that this data over here is very different in these sort of features, and that's why it gets a different label. So that's why I really like to bring an example, because machine learning in a way sort of mimics the way that we learn. And we learn, as a child you learn that these are houses because they have these certain features, and because someone told you that these are houses, okay? So, what is machine learning? So Arthur Samuel, sort of the godfather of machine learning, he coined the term. So it's the field of study that gives computers the ability to learn without being explicitly programmed. And Richard Bellman had a really good quote that I like is, it's the automation of activities that we associate with human thinking, activities such as decision-making, problem-solving, and learning. So instead of having a human make a decision about buy or selling stock or some other sort of a business type decision, we train a machine to do it using data. We're not using code to train a computer, we're using data. And that's the key difference between machine learning and computer programming. Okay. So what are some examples of machine learning? So examples in the form of data are passed through algorithms that look for patterns in data in order to make predictions and decisions on future data. A computer observes data of a certain category and that exhibits certain characteristics of another category that exhibits a whole set of different characteristics. So like I said before, it allows the computer to properly classify the data without that labeling. So this is some data right here. We have three images right here. We have two faces and we have not a face. So we're going to train, so in this case we're training a machine learning model to recognize a face. So we tell the model, hey, that's me right there, that's a face. Katy Perry, that's her face. And this is a fidget spinner, not a face. So the point of that is, we train this model to be able to predict on future data that's unlabeled, such as the Golden Gate Bridge and this really generic face right here. So we train the machine on all this data right here, and then we feed in the pictures of the Golden Gate Bridge and the face right here, and then it makes a prediction of whether or not that face or the Golden Gate Bridge are actually faces or not faces. Okay. Oh, by the way, all the materials can be available online, so you don't have to keep taking pictures, and it's also just FYI. So what are some prominent examples of machine learning? You probably encounter them every day in your life. If you're on Spotify or Netflix, you are encountering machine learning every minute you are on that platform. So Netflix and Spotify recommendations, credit card fraud detection. Fraud detection is a big application for machine learning. There are startups out there whose full job is to consult with companies and to make models that predict fraud. Loan approvals. Lending Club is a big tech company, a peer-to-peer lending system that uses machine learning, and they have a public data set that you can use to make machine learning models with. Zillow's as estimate. If you've ever bought a house, or you just you like to look at how expensive houses are in the Bay Area, you see that this two-bedroom, one-bathroom house in the middle of nowhere is going for $900,000. Well, Zestimate is making a model to sort of estimate how much that house should go for based on a whole bunch of different features. Email spam prevention. You may have noticed in your email inbox there are a lack of, you just want $2 million, come collect it from this Nigerian prince, and all sorts of spammy messages. Well, Google embedded or Gmail, whatever email service you use, embedded a model to be able to classify messages that things are spam versus not spam. All those personal system machines, Alexa, Siri, Google Home, those are all trained using machine learning as well. And crime pattern detection. So those are some of the examples that I like to bring up when people ask me, what are examples of machine learning? So what are the two types of machine learning? We have supervised versus unsupervised. So the main goal of supervised is making predictions or classifications. And unsupervised learning is more for finding structures. It's more sort of a exploratory data analysis as opposed to supervised learning, where the explicit goal is to make decisions, predictions, and classifications. Okay. Any questions so far? Usually at this point I have about like 10 questions, but it seems like things. If I'm going too fast, please raise your hand as well. Yeah, I'm going to go that later in the presentation. There's going to be a couple slides on this supervised learning. So, okay. But first, let's go over supervised learning. Okay. So, like I said, the main goal is making predictions and classifications that uses past data to predict the future. Data is composed of observations, events, or instances. We have our predictors, that's aka the X, aka the independent variables, aka features, inputs, their attributes. A lot of times in machine learning, you'll have like 8 different terms which just mean the same thing. Features, that's basically just the columns, okay? And then we have the response variable, the y, the outcome, the label, the target, the dependent variables. Think like a math formula. You have b times x plus intercept equals y. The y is the dependent variable in this instance. So this is sort of a typical machine learning data set. If you have not seen the iris flower data set before, get used to it because you're going to see it in a lot of introductory machine learning repos, courses, and other sorts of materials. So in this data set we have each row is an observation, it's a flower. And each column is a feature or an outcome. So the first 4, from here to there, those are our 4 features: the sepal length, sepal width, petal length, and petal width. And then the species, well, that's our target variable, that's the outcome. So what we would do in this case is we would train a machine learning model on these features to be able to predict which type of flower a given flower is. So we made a model of this, and then we said, okay, we're going to feed in some new data of this flower with unknown label that has about 5 sepal length, 3 sepal width, 1 petal length, and 2 petal width. And the machine learning model is going to look at that, okay, based on that data, I'm going to say that it is a Setosa or Virginica or something else, okay? So what are the types of unsupervised? We have classification versus regression. Classification just means we're predicting categories. It's either or, but there's also multiple categories, 3 or more as well. In this case, we can have labels such as good or bad, 1 or 0. If you're classifying articles, you can classify sports versus tech versus politics versus style. Some common algorithms that you see with classification are logistic regression, naive Bayes, k-nearest neighbors, which is the model that we'll be using later on in this presentation, and decision trees as well. Regression is linear regression. Some people might notice, but linear regression is actually considered machine learning, even though it's more associated with statistics. So regression, we have a continuous outcome variable. We have a bunch of numbers like these, right? And some typical algorithms of regression, where you have linear, you have ridge regression, lasso regression as well. There's also decision tree regression as well, and k-nearest neighbors regression. Okay. Here is a very good example of a supervised classification example. So we have a problem. Lenders lose money when loanees fail to pay back loans. So the goal in this case is to develop a system that can officially identify high-risk loans so lenders know which applications to reject. So the data that we're using in this case are records of previous loans marked as successful or failure. That includes relevant information such as income, credit score, loan term, loan amount, etc. Are there any other features besides the ones I mentioned that you think would be useful in predicting whether or not a loan is successful or not successful? Yeah. It's a default, yeah. That probably correlates well with whether or not someone will probably default on a future loan if they've already defaulted on a previous loan. Anyone else? Yes. Yes, income as well. Oh, there's it? Okay. Well, type of employment maybe as well. No. Debt, yes, previous debt. Do they have debt or not, or how much debt do they have previously? That's probably a good indication of whether or not. And you? Credit score, yes. I got that. I have that. But yeah, credit score is obviously a good feature. Okay. For the regression example, we have housing prices. Okay? So the problem here is a homeowner wants to sell her home but can't decide on the asking price. So the goal of hers is to accurately appraise the true value of a property. The data in this case is previous home sale records labeled with their sales prices. The data set features includes number of bedrooms, number of bathrooms, square feet, location, years sold, etc. Can anyone think of any other features that would be important in making a linear regression model to appraise a home's value, besides the one that you guys already went though? Anyone else? You confirm. View, yeah, okay. That could be a dummy variable. We label it view or not view. Black, blue jacket. Okay, yeah. Exactly. Values of homes in a neighborhood. Chances are, if you have a 2-bedroom, 2-bath in one neighborhood, the house next door that's also 2-bedroom, 2-bath, probably has a price within 100,000, maybe 50,000 of that other house. Yes, you? Exactly. That condo versus townhouse versus home, etc. Those are good features to have as well. Purple. Exactly. Those are more features that we get, especially in California. There's enough houses with swimming pools that we should probably account for that in any sort of model that predicts housing prices. And your last one. School district as well. Okay. How would you? Then that's sort of a tricky question. How do you rate the school, the quality of the school as well? So that's very important too. A lot of homeowners have kids who want to live in neighborhoods with good schools. So I get. Yeah.
So the previous example, though, could be a continuous outcome if you did something like what was the risk, default risk versus should I reject them or not. So I'm wondering if the examples they're giving, like you can probably express them in both regression and classification outcomes.
Yeah, that's definitely, you can do that as well. So, and even with this case, with regression, you can just say $1 million house versus non-$1 million house. So you can sort of, or if you're predicting movie revenue, you can just say whether the movie will be profitable or not profitable. So there's definitely not like a firewall between classification and regression, but it depends on you, the data science, whether or not you, the context of the problem that you're working in, do you want to have, is your goal for classification or is it regression? Do you want to just predict an outcome or an actual number? So so like I said, yeah, you're right that there's not really a firewall between the two, but it really depends on the context that you're working in. So any questions about those two examples? I really like them because they really cut to the core of a supervised learning example, two different supervised learning examples. Yes? Yes. Yeah. Yes. But machine learning looks at the past data, and then when it looks at new data, if it notices any sort of similarities and patterns between the new data and the old data that's pre-labeled, it makes a classification on the new data. And we'll get more into that later with the actual scikit-learn demo. Okay.
So do you need to weigh the features, or does the machine do that by itself?
Do you mean like standardize or scale or?
Maybe bedroom and bathroom is more important than the years old, and so would the machine understand that by itself?
That depends on the algorithm that you work with. Some algorithms will weigh the features themselves. Like logistic regression assigns coefficients to different features. To tree-based models sort of rank features as well. So it's a good question. Some models assume sort of each feature has equal importance, and some others actually sort of make a ranking, like you said, of the importance of that feature. That's a good question as well. Any other questions before we move on to unsupervised learning? On your left, actually.
Was the first example of classification because the outcome is default or not?
Yes.
And then the second one is predictive.
Yes, because we're predicting a number on it's continuous. Okay. So the classification, the outcome that you're predicting doesn't even have to be a number. It can just be just actual labels, good or bad, yes or no. So let's move on to unsupervised learning. And if there's one thing we take away from this presentation is that the difference between unsupervised and supervised is that unsupervised does not have any labels. There are no outcome variables, there are no target variables, there are no labels. And that's why it's unsupervised. Labels do the supervision, So if there's no labels, then it's unsupervised. And the two types of unsupervised learning that we have are clustering versus dimensionality reduction. So the goal of supervised learning is sort of find groups of observations that exhibit similar characteristics, and find combinations of features that explain the variation in the data. It's useful as sort of a pre-processing exploratory data analysis. With unsupervised learning, the goal is not as explicit. You're sort of just getting a feel for the data. You want to sort of get to know it more. You sort of go in there, I wouldn't say totally blind, but you don't exactly know where your path is going. Whereas with the examples I gave with supervised learning, we had a specific goal, and that was to predict loan defaults or predict housing prices. And we had a clear-cut plan. And supervised learning is not as tangible or sort of direct as supervised learning. So the two types, like I said before, clustering versus dimensionality reduction. Clustering does that. It clusters data into groups. It makes labels from unlabeled data. So a lot of machine learning, some companies will actually use unsupervised learning as a means to supervised learning. So let's say you're a social media network, you're just starting out, you have a whole bunch of users, and you want to get to know your users. So you run these clustering algorithms, and they determine that there's 4 types of users, okay? Then, once you decide on those labels, every time you get a new user, you can automatically use supervised learning to classify them as one of those 4 different labels that you predetermined. Okay. Another example that I like of clustering is deriving the micro positions in sports. There's a really great project I saw recently where this guy used clustering to come up with 15 different micro positions in basketball, and he classified every NBA player as one of these 15 positions. It's a great project. Some common algorithms that you see with unsupervised clustering are k-means, hierarchical, and DD-scan. Okay. And dimensionality reduction, it does that as well. It reduces how many dimensions that you're working with. So imagine you had data with like 200 or maybe 1,000 columns. Now what if I told you you could compress that data down to maybe two columns or 3 columns, and you can visualize that data. And that data captures a significant amount of the variance, or like the essence of that 1,000 dimension data. Well, that's what dimensionality does. It's, like I said, it reduces the dimensions of data while still capturing a certain amount of the variance, or sort of what I like to call like the true self of the data. And I like to use it when I want to visualize high-dimensional data. So if I have 10 dimensions, I want to put this data on a 2-dimensional plot. Well, I can do that using PCA algorithms such as PCA, truncated SVD, and non-negative matrix factorization. Who has a question about unsupervised data? Okay. So does that answer your question? Okay, this group, did I go too fast?
I'm sorry, no, I think you were mentioning how you would sometimes use this and then send your stuff yourself up to the first.
The example about the social media company. So that was it. So like so you have your new company, and you don't have any labels for your data. You sort of still getting to know the data from the users. Let's say, okay, let's cluster them, and then we get 4 clusters. And then later on, when you get new users, you can train a model to automatically classify those new users. Okay.
So those 4 clusters, you would then name them.
Yeah, exactly. Yeah, you would have to come up with it as a data scientist. You would have to do some sort of data analysis and say, okay, cluster A is, we're going to give it this name, and then we're going to give it this description, because this type of user or sort of phenomenon is happening with cluster A, and same thing with cluster B, cluster C, cluster D as well. This brings us towards the end of the presentation part. I'll take a couple questions about this presentation, and then we'll move on to the scikit-learn demo. Any other questions? Yes, Matt.
Can you define supervised and unsupervised learning?
Okay, Okay, so the difference between them, well, I like to define them as sort of mention the difference between them. So the supervised comes from the labels. Supervised learning, we are predicting an outcome or a category or a sort of a target. Unsupervised learning does not have that. It's all X variables, only features. We are not making a prediction of we're not predicting loan defaults, we're not predicting housing prices. We want to get to know the data better. We want to make labels from that. We want to make clusters from that data. Whereas supervised learning, we are explicitly classifying or predicting a given outcome that is predefined. Does that answer your question?
More or less, yeah.
Okay. Well, the key thing to remember is that there are no labels, there's no outcome in the unsupervised, whereas supervised does have labels. And that's why it's called supervised. Labels themselves are due to supervision. So if you take anything from this presentation, just know that's the main difference between supervised and unsupervised learning. Yes? Yeah, the outcome is labeled. So it's like I said before, sometimes you'll have like 6 or 7 different terminology to describe the same thing. So labels, dependent variable, outcome, target variable. There's probably a couple others that I've seen all the time. The Y variable in a formula, those are all the same thing. Okay. Yeah, that makes that supervised learning. When you have that Y variable, that outcome labels, that pre-labeled data, that's what makes it supervised learning. There's no label. That's why it's unsupervised. There is no label. Yeah.
Make sure I understand. An example would be like if you have a bunch of pictures labeled cat, you want to train it to recognize cat, that would be supervised.
Yes.
Whereas if you had a bunch of pictures of different animals, you want to cluster, these are cats.
Exactly. So the
it doesn't
machine
know what they are.
Yeah. So the machine would get a bunch of pictures of animals. The machine would figure out. So it might do a good job of being able to figure out, okay, this is a cat, this is a dog, this is elephant, and so on. Whereas supervised learning, we would feed in a bunch of pictures that we labeled as cat, dog, and so on. Who here watches Silicon Valley? You remember the hot dog or not hot dog app? Well, that's machine learning. They had to get a bunch of pictures labeled as hot dogs or not hot dogs. And they fed it into a machine learning algorithm, and that was it. So then they point your phone at a hot dog or not hot dog, and then it makes a label. That is a very basic example of machine learning. And the back of the hat. Yes, yes. Like a lot of times companies will do that. They have a bunch of data that's unlabeled, so they use clustering or unsupervised learning to make those labels. I don't know if you heard the example before about like a social media, like a tech company that has a bunch of users. Let's say those users come unlabeled, so they need to make those users, turn those users into clusters. And once they have those clusters and they define them, then they can train an algorithm to automatically classify new users that they get into those 3 or 4 labels. If you have any more questions, you can find me after the presentation, but I think it's time to move on to the scikit-learn demo. So show of hands, who here has this screen? And also, who here plans to follow along and code along the presentation? Most people, okay. So I'll give you a couple minutes to get this ready.
Where's the link for
Where
this?
to get to that?
GitHub? Is it under your GitHub?
Did they send out like a?
Is it under here?
Yeah, that's the link right there. Okay.
So if they go under So Demystifying Deep Learning AI, they scroll down and they click on your present.
Okay.
It's like under additional presentations.
Okay.
Yeah.
So go to the Excel AI GitHub page and scroll down, and you should see my name, George McIntyre, and then /intro_ML presentation. You'll need to clone that repo onto your local machine, and then you'll have to open up a Jupyter notebook. Shouldn't take too long, it's not a lot of files, so the website, or you can go directly. I don't know if you can see this well, but if you go to github.com/my name George McIntyre right here, /intro_ML_presentation. You go there, click clone or download, and then you copy this, and you go in your terminal, and then you can you clone it into a directory where you want to put those files. Raise your hand if you need help. If you don't know what I'm talking about. Okay. So I'm going to do a quick little tutorial on how to clone a repo.
We're also going to put it in the Slack channel, the direct link to his repository.
So open up a terminal or a command line, but not depending on your PC or Mac. You're going to type in git clone and then copy paste the link that you get from clicking this. So you click on clone or download, then click copy to clipboard, go to your terminal, and then do git clone and copy paste the link to the repo right there. But first, go to a file or directory. Go to a directory where you want to put those files. You know where they are. I hope that's big enough to see. Okay. So once again, go to the repo website, click clone or download, then click copy to clipboard, open up a command line or terminal window. You're going to type in git clone and then copy paste the link that you copied from the GitHub repo. Raise your hand if you are on the Jupyter Notebook page and you're ready to go. Okay, so you go to the GitHub repo page. Yeah. Click. Yeah. To desktop. Okay. Okay. So once you've cloned it, click clone, and then you'll have to cd into that. So you can do cd intro the ML presentation, and then you're in there. Am I answering your question? Your hand went up and then went down. And then once you're in the directory with the presentation materials, you type in Jupyter Notebook. And then that will launch, open whatever your default web browser is. And then you'll see a directory with the files, and then click on Scikit-learn demo. Do not click on Scikit-learn demo completed. You just do sklearn demo. Alright, I can only do this for another couple of minutes because we got the presentation. Yes? We can't spend any more time on the installation. So if it's not working, you can go to the GitHub repo website and just click on Scikit-learn demo. You can follow along. You won't be able to run code, but you'll see the code that you'll have the code for yourself. And I can help you later on today. I can help you install that if you need it. But unfortunately, due to time constraints, we have to move on to the actual presentation. Okay? So first thing we're going to do, we're going to run our imports. Over here, we're going to import pandas, NumPy, and we're going to import a bunch of tools from Scikit-learn. That is the main Python library for machine learning. And so today's machine learning algorithm to learn is k-nearest neighbors. It is referred to as the easy machine learning model, hence why I'm using it in this presentation. So what it does, the way it works is it classifies an event or a piece of data based on its closest relatives in the data the model has already been trained on, hence the term nearest neighbors. The k equals the number of neighbors predetermined by you, the data scientist. It's also known as a voting classifier. And what that means is, if you feed a new piece of data and it's similar to about 5 different other pieces of data, and those pieces of data say label A, well then it's going to classify the new data as A. And I'll get more to that when we actually do the coding later on. So what it does, the mathematical foundation of k-nearest neighbors is the Euclidean distance function. It may sound complicated, but all that does is calculate the shortest distance between 2 points, a line. So the pros of k-nearest neighbors, it's fast, it's intuitive, so it's just easy to interpret, and it has a decent, it's pretty good at making probabilities. The cons are that it's poor at handling many features. I wouldn't really use k-nearest neighbors with more than double-digit features. That's just my opinion. It's really good for data that has, 3 to 9 or 2 to 9 features. And it's not good with small sample sizes. You really need to have at least maybe like 1,000, at the bare minimum, 1,000 rows of data for a k-nearest neighbor algorithm. So this is the Euclidean distance function. You may recognize this because it's basically calculating the hypotenuse of a right triangle right there. So as we know, the hypotenuse is calculated by x squared plus y squared equals a squared plus b squared equals c squared. Well, to find the length of that, you just take the square of a squared plus b squared. So this first part, no one's getting that graphic, good. Okay. Okay. Well, okay. Well, the good news is it's not the only Euclidean distance image out there, so if you need this, you can search Google for it. So the first up, we're going to make some fake data. Data just means nothing. And we're going to visualize it. So run this code right here, then fake data, and then run the code below that. We're going to separate the data into features and into labels. The X is going to be the features and the Y is the labels. And then we're going to plot this color-coded data. The color code comes from the label. So run this, and what do we see here? Okay. So we see any patterns in the data? Okay. Anyone have any interesting observations about the data? So with this, yeah? Well, when this data, the goal of this data is we're trying to predict points that are either blue or red based on their position on the x-axis and the y-axis. And we see sort of the west part is sort of more blue and the east part is more red. In the middle, we have, it's really mixed up right there. But we're going to try to build an algorithm that can basically predict new points as either red or blue.
Supervised.
Yeah, this is supervised because there's labels. Again, we are doing supervised learning because the labels in this case are blue versus red. So this is how we use, this is how we call the k-nearest neighbors algorithm. We are going to initialize it here. We're going to say k and n3 equals k neighbors classifier, and within that algorithm we're going to specify n underscore neighbors equals 3. So now we have a blank k-nearest neighbors model with a specification of 3 neighbors. And below that, we are going to fit the model on our data, the x data, the two-dimensional x data, and the y data, which is the labels of red versus blue. And then after that, we're going to score the data. So once we've trained our algorithm or fit our algorithm, we're going to fit in all the data, and we're going to make predictions on that. And then in data, we're going to score how well the data did. So which is basically the accuracy score. So if a data point is red, and the machine learning classifier says it's red, then it's 1. That's one correct prediction. And it takes the sum of the correct predictions and divided by how many predictions we made total, and that is the accuracy score. So run this code here, and our model says that it accurately labeled 93.5% of the data. That's pretty good, I'd say. So just to go over this one once again, we initialized our machine learning algorithm, k-nearest neighbors, with a specification of 3 neighbors. We set that equal to a variable called k-n3. After that, we fit and train are basically 2 interchangeable terms. That's basically where the learning happens, basically. The model is learning from data when you fit the data on the x variables and the y variable. After that, we have a trained model. And the third part, we are scoring it. We are taking in the data, the features and the labels, it's true labels, and we're scoring it. So what the model is doing is making predictions for each row, and then the score calculates whether or not it got it right. So in this case, 93.5% of the rows were accurately labeled as blue or red.
Yeah, it's kind of like residual from the sort of.
Yeah, it's sort of it's more or less the same. Yeah, it's the residuals. Go ahead and put it. Yeah, because it's sort of that is basically the regression version of what we're doing. Yeah. In this case, we're not going to calculate the distance between like predicted versus actual value. We can just say yes or no, and then sort of sum that up. Now let's try this with 5 neighbors. Anyone want to guess why I'm using odd neighbors as opposed to even neighbors? Not better accuracy.
The great guys.
Yeah, exactly. If you train a model with even neighbors and the neighbors say it's evenly split, well then your computer breaks, and then you rip a portal in the space-time continuum, and then the Earth gets eaten by a black hole. So just a good practice is use odd neighbors. So let's try with 5 neighbors. This time, the accuracy of our data actually decreases. Now I'm not saying that more neighbors equals worse models, but that's just this instance. Sometimes you can have a neighbor, models trained with 313 neighbors. That can be really good. But think about how, if you increase the number of neighbors, how much farther you're getting away from a certain point. So if you, yes? What's the error? Are you on Python 2 or 3? 3, okay. So if you're on 3, put this in parentheses. So the update that they made with Python 3, now when you have to make a print statement, you have to put the thing that you're printing in parentheses. Yeah, so I forgot that with the 5 neighbors, but I did it with the 3 neighbors. Okay. So with these 2 algorithms, we made predictions on data that the algorithm has already seen before, and so that is a form of bias, and we'll get into that later on. So the true test of a model is how well it does on data it hasn't seen before. That is how well your prediction is. And sure, you can make predictions on stuff you've already seen, but you're really only as good as predictions on data you haven't seen. So what I have right here in this code is, I have this point right here called new data, and I'm passing it in to the KNN3 model, and I'm passing it in on the KNN5 model, and I'm making a prediction. To make a prediction, you just call a .predict on the model, use that method .predict, and you pass in this new data right here. And we're going to see what KNN3 thinks of that new data, and what KNN5 thinks of that data as well. So let's run that. And it turns out that KNN3 thinks that this data should be classified as class 1. And KNN5 thinks that should be class 0. So it's sort of puzzling, right? It's like, why is it, how could this point be classified as two different categories by two different, not that different machine learning algorithms? Well, let's visualize that. Let's visualize this new point on our graph, and then we can sort of do an eye test and make our own predictions. Okay, so that new point is the purple star in the middle. Now imagine yourself as the model that's trained with 3 neighbors. So try to find the 3 closest points and then make a prediction on that. So what do you think are the 3 closest points to the purple star? So people are saying here. Okay, so I guess, so based on the 3 closest points to the purple star, should you classify the purple star as red or blue? Okay. So like blue, we have I heard a bunch of reds, a couple blues. I think it's blue, okay. Yeah. So I think the reds have it, actually. So if you look at the 3 closest points, and then we tally up their categories, we're going to see 2 reds and 1 blue. So what the KNN does is, okay, since those are the nearest points, and the voting tally, that's why it's called a voting classifier, because the labels of those 3 nearest points voted for red. We're going to classify this new point that the model has never seen before as red. Now let's do this for 5 nearest neighbors. Look at the 5 nearest points. So you already didn't have to work. We already know the 3 nearest points are. So what are the 4th and 5th nearest points to the purple star? So is it this 2 right here, or this, or? So are we saying these 5 are the nearest to purple? Okay. So it looks like in this case, the blue dots won. So the voting in this case is 3 blue dots to 2 red dots. So that's why, as we saw earlier, those 2 different algorithms make 2 different predictions on the data. KNN3 said this new point is red, but KNN5 said this new point is blue. Any questions about K-nearest neighbors, this visualization, or anything I've done so far in the scikit-learn demo? Yes?
So, in real world, in real life, how do you judge what the case will be if the number, if the prediction keeps on changing? How do you justify what you do?
That's a good question. So your question was, so in the real world, how do we choose the right K value when it comes to predicting new data? And if we have time, we'll get to this later in the presentation, but what we cover later on is sort of how to make evaluating machine learning models based on data they haven't seen before. So if we get to that, I'll answer your question. But if not, find me later and I can answer it for you. Okay? How much time do I have?
It's 11 now.
Okay. So we do.
Can we do a few more minutes, please? I don't know.
Can we do one more thing?
Yeah, sure.
Okay. So So this next part I'm really excited about is, so we can see the data, but what if I told you there was a way we could see the actual model? What do you think I mean by that? Like seeing the model. A model that makes predictions of red versus blue. Say it loud.
The logic behind the complementary.
So you're saying like the logic behind that? Is anyone, you?
You do an area graph more or less, like these regions would be red.
Exactly. That's exactly that. So we're going to visualize the model. The model is going to sort of tag the whole graph that we saw earlier as red or blue. So ignore this, watch this code right here. This basically just allows us to do that. So make sure you run that function, and then we're going to put in our model here, the x data, the y data, and specify the 3 neighbors. We run that, and who wants to tell me what's going on here? You're in front. Yeah, so it's making decision boundaries. So if you look in this lower left corner here, this whole area is red because of these 2 dots. So at any point that falls in here, the 3 nearest neighbors, 2 of them are going to be those red dots. So at any point that falls here, it's going to be classified as red. So the blue shading, the red shading, that's the model. That's the model saying whenever a new data point falls in this area here, it's going to be classified as red or blue. And if you zoom in, you'll see some red dots in the blue areas, and you'll see some blue dots in the red areas. Now you see this red dot here. Well, it's in the blue area because that red dot, poor little red dot, was outvoted by its blue peers. So if you have a new point next to that red dot, it's always going to be classified as blue because you're always going to have more blue dots in that area than red dots. And the same thing over here with this blue dot and the sea of red. So that's it for 3 neighbors. Hold on a second. Let's try this again with 5 neighbors. And we see that this little oasis of red is gone because 2 is obviously not a majority of 5. And we see that the boundaries between the blue area in the west and the red area in the east sort of smoother as we add more neighbors. So if I were you, I would sort of go back and forth and try to see this sort of the small differences between the red area, the boundaries in the 3 neighbors graph and the boundaries of the 5 neighbors graph. Unfortunately, this brings us to the end. You can take a couple questions. I know you in the front have one, and then I can take a couple more after that. Not necessarily. I mean, then you can only work with the features that you do have in this case. But it's up to you to sort of explore what is the right number of neighbors. So if you're classifying animals that will yeah. Yeah, exactly. So sometimes that is multidimensional data because we're dealing with pictures here. But if that was in a tabular format, sometimes an algorithm, if there's a bunch of zeros in that row or something that a bunch of data hasn't seen before, you may not know what result you kind of get. So that's just sort of if you feed in data that the algorithm has really never seen before, it's really different. You can get some sort of wild results or something. But yeah, more questions before we about the whole presentation from start to finish. Going once, twice. If you have any more questions, you can find me later. I'll be happy to answer them. Yes, you.
How do you perform this
It depends. More neighbors doesn't mean better performance. Less neighbors doesn't mean better performance as well. It's really depends on the context that you're working in. It depends on the data you're working with as well. Whether or not more neighbors will equal better data. But think about this. If you have a model that's specified as 503 neighbors, well, you're going to get some neighbors that aren't really that similar to some of your data points. You'll get, if you had So this is about 200 points of data. If you did 100 nearest neighbors, well, if you have like a point over here, the 100 nearest neighbors to that point where my mouse is, they're not going to be really that similar to that point. So you're sort of adding in some biased or junk data when you have more neighbors. So it's not, how similar can you get if you are looking at the 107 nearest neighbors to a certain point?
Actually, I want to know how much computing power if I one neighbor again.
There's none. Yes, I don't think there's in terms of computing power, I haven't really noticed that. I don't think, the boss says that there's no difference. So she's the authority on it. Yes?
So for and just to kind of summarize what you said, if I have 3 to 9 or 2 to 9 features,
Yeah.
I can do this for that. I can do this one outcome.
Yeah.
Then KNN will work well.
Yeah.
And I can use this. I can use what program to do this. This is in GitHub, but it's a set of commands that are.
You mean the plotting?
Yeah. So like if I have my own data set, I want to.
Yeah. So you would use Python, specifically the scikit-learn library. That is the Python's machine learning library. I use plotting tools such as matplotlib to make this chart right here, and the data was stored in pandas and NumPy. So those are like the 4 main Python data science libraries: pandas, NumPy, scikit-learn, matplotlib. There's also Seaborn is another visualization library, and then you have NLP libraries such as NLTK, Jensen, and TextCloud. I believe that's it for me. Do you have any questions?
I can't visualize like 8 dimensions in the same way.
Oh yeah, I don't think there's any. Has anyone come up with that?
Not
Visualize 8 dimensions yet? I don't think
8
so.
dimensions.
Or yeah, I mean like, but this is great. This is cute. But if you had more, you would have like.
Yeah. So exactly, that's sort of the problem. That's why I like to use 2 dimensions, because we can actually visualize the machine learning model until they invent a way to visualize 4 more dimensions. We're going to be stuck with visualizing. You can also do this in 3D version as well. There's some programs you can do that with, but unfortunately we cannot visualize more than 4 dimensions. Okay.
You said 5 libraries. Where is one of them? Other NumPy,
Seaborn and Matplotlib. Okay. Well, that's it for me. Thank you for joining me for Introduction to Machine Learning. If you find later, you can ask me a question. But my name is George McIntyre. Thank you.
Thank you, George. So we have Panjak Kumar, coming up next. We're going to let him set up and take a 5-minute break to do a bio break, get some water, some coffee, whatever you need, and come right back for image recognition. Image captioning in TensorFlow. Yeah.
Down somewhere, walk to the back. Green dress. Oh yeah.
Wait.
What's your name?
Sarah.
Great. Thanks so much for coming.
Support.
Next speaker, Sarah.
Oh, hi. Really nice to meet you.
Good to meet you too. You're going to be going on this afternoon?
11:15.
I know what happened. There was confusion with your time, and I emailed you about this. Are you
Just the day. Let's double check. It's cool enough though. I love the space here. This is so neat.
It is really nice.
Download the live install.
Yeah, I've been If that's the case, I just want to make sure you guys have my PowerPoint as well.
Yes, we do have your PowerPoint, I know that, so that's not a problem.
Let's see. Huh.
One more second.
Yeah, no worries. Yeah, I just want to double check too. If I put it wrong, then I can. Otherwise, I just get a preview.
So then I didn't get one back from here. Oh, no. Yeah, so I just
Yeah, because
you may have emailed her directly, not me, which could be the case.
what do you suggest? So for yourself?
Well, I want to make sure that we get your talk in either way. So I would say, what would be the best for your schedule right now?
Let me pull up on my laptop. What time do you have that on the calendar? Because I didn't just out.
I think we actually put it on for tomorrow, which is one.
Tomorrow's my last day at my office, so I definitely have to do it.
Right. So I'd say let's get it in today. So you said you're meeting at 1 o'clock.
Yeah, I got it from that one.
Oh, I know. That's okay. His presentation is only going to take half an hour. Okay. So we can have you go right afterwards, and then I can do this again.
But it's a basic about they're going down. But really,
No, that's fine. We're on a break anyway. So you have something at 1, something at 5. Okay.
I don't know if I talk really longer than like 5 minutes, so that's
We could have you go.
okay. Awesome.
Should I just install again? You asked me to do that for this. Okay. So just Google Git installation. Okay. Do that. Windows. Okay. Anything else I should install? Just get ready for like the later parts. Do that. Do that.
Right.
Yeah, no, sorry about this.
Oh no, no problem. I'm sorry too.
Okay, cool. What's this talk?
He's doing image capture and TensorFlow. Exactly.
Well, thank you so much for having me.
There's pictures all the way around in the back. You can go either way too. Okay, great. Thank you so much. No problem. Thank you.
Who's the person who can help out install things?
There's several mentors. Candiva and Bethany are the main ones. You have the live session. But who has a question?
This guy.
Is there like a hard copy or sure the program?
So we have it on the so that same GitHub where we have the download and install instructions, we have it on the app. Yeah, the link to it? Oh, you just want to look at the schedule.
So tomorrow it ends at...
So tomorrow, our lightning talks are closing at 4 for the closing remarks, and we have a little networking session.
What are the lightning talks? Okay, thank you so much.
Okay, we're going to ask people to come back to your seats. Our next speaker is ready to get started. Okay, so we want to thank our next speaker. Pankaj Kumar is going to be covering image captioning in TensorFlow. Please give him a round of applause.
This problem, you see, like given a picture, the viewer should be able to tell what is in the picture, should be able to describe the picture.
More angled towards your mouth. Can everyone hear it okay? Sort of? So yeah, try to project a little more, hold it closer.
Sure. Okay. So this problem, I could never see like a linear method tackling this problem because given a picture, to be able to explain what are the contents of the picture. So this got me very interested into neural networks. So let's go through I'll go through what are the building blocks behind the solution to this problem, and then I'll show you a couple of implementations. So the first building block is just neural networks. So neural networks are the main difference between neural networks and the previous methods, the machine learning methods, is that neural networks are non-complex. So what it means is like when you try to figure out which is the best solution, like it's in a let's suppose a 2D or 3D plane, then in linear methods, generally the way the problem is formulated, you start at a point that loss is always going in one direction. But in neural networks, you can have like a zigzag loss function, and which is they call non-convex, and you can start at a point, but this can model many the actual relations. So, for example, if you see a graph, right, the relationship between input and output may not be very simple. It could be very complex. So, neural networks model those relationships better. And for example, here, if you see this left method, it could take a three-dimensional point and classify it. For example, in the previous talk, we had blue and red dots. So it could take points and it could classify them as blue or red. It could give you a probability of a blue or red point. So given a new point, when you say instead of giving a nearest neighbor, it will actually go through, run the neural network forward pass and tell you what the probabilities are for the point being a red point or a blue point. So this is how neural networks can have multiple layers, which increases the capacity of the network, which means it can model a more difficult talk. And model a better problem that has a more complicated relationship with the so for example, in a 3D, if you have a 3D point and you have like a bunch of red points here and a bunch of red points somewhere else interspersed with blue points. If you try to make a linear separation between them, it won't be possible. But here it can do it because this has more capacity. It can actually figure out okay, is a particular cluster in a particular place, and it can model a more complicated relationship. So that's this is comprised of a bunch of neurons, which are neurons, hidden layer and an outer layer, and each of these hidden layer and so these lines are a linear transformation on so if you, for example, put a 3D point here, these will be like just multiplication of these numbers by particular weights. But these transformations from here to here are generally non-linear. So it means it's like a sigmoid or it's a value or something like that, so that it can that gives the capacity to this part. If this was linear, like if this was again linear, then the whole model will become linear in the straight line through the points. So it won't be very easy. But when it comes to image classification, this model doesn't work very well because the problem is image is a very high image. If you have like a 256 cross 256 image, then it will be like a 4 or 5 inputs. So this model is not very good at modeling images. So there is a different kind of neural network called convolutional neural networks in which you take an image and you take a filter. And this is just a filter. And this is like a smaller set of weights. So this can be like this is a 224 cross 224 cross 3 image. Then this can be like a filter can be 5 cross 5 cross 3. And these are the only weights that you have. And then what you do is you dot product. Dot product means element-wise product and summation. So you can get one number out of dot product. You take two vectors, dot product, you get one number. And you take this filter and you apply it to the top left corner, and you move one, you slide it to the right, apply it to the next part of the image. So that way you get a bunch of numbers again from these filters. And those are called activations. And using this, you can have a smaller number of things and still have a function that is differentiable. You can use it to train a neural network. So this is very widely used in image classification. So and the results.
Just make sure I understand. So you basically say you have like a 10 megapixel picture, right? You're using this convolutional layer to downsample that to, I don't know, like a 10 by 10 picture or something.
It's not downsampling. So there is some downsampling. So max 2 is, for example, a downsampling. But convolution itself is not downsampling. It's like transforming the image into activations so that with a limited number of weights. So see, the problem here is that if you, for example, have 10 megapixels here, then on the left there, then you will need the weights will become unmanageable. Right? So what you do is instead of carrying forward a bunch of the whole, if instead of doing a feed forward to each point, you actually take a filter, and you just so another analogy is that the first filter will figure out if you're, for example, trying to figure out whether this picture is a cat, then a filter will tell you whether it has whiskers and whether it has an ear. One filter will model whether it has whiskers, the other filter will model whether it has ears. It's like a very bad analogy. It's not exactly how it works.
So I think I can kind of make it more clear. Is it that each of these filters sort of has an understanding of what an edge or a whisker something already looks like, and it's looking for it, taking the data from the attendant console and
You can think of it that way, but yeah, it's not exactly that. So it's like it's a good way to understand it, but the way it actually works, even convolutional layers have multiple layers. So the first set of filters figure out very simple patterns. The second layer can build on top of it and can understand more complex things. And the third layer, and the final layer can actually tell you whether it's a cat or a dog or something else.
convolutional layer is itself with multiple layers of clues or edges or things that picture might contain to get to that final determination of what is happening.
That's right. So if you see here, there are multiple convolutional layers. So there's a CON64, CON64, so this is like the neural net pipeline. So like the image starts here and then goes to a convolution, 64 convolution, and then another convolution. The max pool is actually downsampling the output at a time. So it goes one after the other. And actually, even at the end of this, you again have a fully connected layer. So this is a fully connected layer. So you again, after convolution, like your picture has been downsampled into like a smaller space, and you put a fully connected layer to figure out these properties of what the picture might be. And if you see here, like before the classification errors, so 2012 is when AlexNet came out, and AlexNet is the used convolutions to do image classification. And that year, after that year, there was a challenge called ImageNet, and the accuracy of the models have been going up quite a bit since 2012. So now there is another sort of problem, like for example, how do you translate the big English in another language, or you give a sequence to Google when you type something, how does it predict what is the next thing that you want? So that there's a different type of neural net called recurrent neural net that is better at understanding these. And the way recurrent neural net works is basically it has it kind of models that the next word, the only thing that what it has seen before. So in here, for example, cat sat on a. So cat sat on a gives all the information it needs to model what is going to come next. So that's what it assumes. So the way it works is you give cat sat on map as input to this neural net below, and this is like a and it outputs the next word. So when you put cat, it will output the next word. When you put sat, it will output the next word. After on, it should output a map on the point. So that's a RNN. The way RNNs work is they have like two matrices. So one matrix multiplies this word embedding to word representation to and then another matrix multiplies this previous value to with that matrix and sums it up to find H1. And then H1 has a transform that goes to Y1, and then the next one can be given. So recurrent neural nets, it's hard to give it really fast, but think of it like think of it like just one matrix being multiplied again and again and again to model the next word given the previous set of words. And but this RNN has a slight problem that if, for example, the matrix that gets multiplied over and over again, right? If, for example, all the values are high, then it will keep increasing with one. So, if, for example, the matrix only had 2s, then if you multiply the matrix by the same matrix again, then it will have 4, then 8, then 16, to grow exponentially. So it's very hard to train. And similarly, if it's a low number, like if it's 0.1, the matrix contains all 0.1s, then if you multiply it multiple times, it becomes a low number. So it becomes harder to train. So better way to do it is LSTM. So LSTMs, the way they work is they do not rely on direct matrix multiplications, but they kind of use the matrix multiplication to pick and choose how much of the previous multiplication equal to the next word and how much can be forgotten. So it avoids that problem of exponentiating the matrices.
What is LSTM stand for?
Long short-term memory. So long short-term memory because in RNNs, if you have like a big text, you can try to remember the whole text and give you the next word. But in LSTM, you have a full stop and it will give more weight to whatever comes after. So that's okay. So Microsoft has this nice data set and called Coco, and it has a picture, and the supervised team has 5 lines written for every picture. It has done it for 120,000 images, and then there are multiple implementations of how to use these to be able to describe any given picture. So this is how we put everything together to constants and RNNs and LSTMs to build this system. So basically, you will take an image, you will go down through this convolution, and you will get like a 4096 bit representation of the picture. And then you feed it to this LSTM, or it's not as an RNN, but and then this LSTM takes it in the initial cell, and then you feed it the start symbol, and it will say, given this, it will say, like for example, it sees there is a hat, and it will say maybe a person with a hat, like it will start off doing that, and then if you remember parts of the picture that it meets across these, remember parts of the picture from there, and it will start outputting a description of the picture on mice. So, and then it will output an end token when it is done. So this is kind of how this image capturing works. Image concept, just on there, you get a representation of the image, you feed it into the RNN, and then it tries to describe the picture to RNN. So you feed it like start token, it will give what is the first word, then first word, then the second word, and describe. So this is a similar image for the same thing.
So the RNN predicts the probability of the next word given all the previous words, right? How does that translate to this notion we're giving it this 4,000 bit integer, or whatever you want to call it, from the first CNN, that has all the information in it. So what does it parse it, like 8 bits at a time or something? Like how does that relate to recurrent?
Sure. So think of it as like image. This 4096 is a representation of the image. 4096 print. Then it gets multiplied by a weight matrix. That brings it down to, let's suppose h is, let's suppose 100 bit vector. Then this matrix will be 4096 cross 10 weight matrix. So there's a weight matrix here that multiplies this output to get to this value, this 10 bit value. And the same way, there's another weight matrix that multiplies this last token to get the next, to get to the edge value. So this, for example, the representation of start is, let's suppose 100 bit. Then there will be a weight matrix that will be 100 cross 100, edge was 100 bits. And then you add those two together. So what it does is it basically takes into account what it needs to remember from the picture and keeps carrying it forward. And those weights are learnable. That's what we're learning. So the weights will be different for every picture. You learn what is the weight and that will be used. This one implementation I have. This is what I've explained in Andre Garapathi's lecture notes. He has a very good course. Like it's all available on YouTube and the website. Just CS231N course. I'm sorry.
Andrew, is that this course?
No, it's from Stanford. His name is Andre Garapathy. It's convolutional networks for something. A lot of this. So I'll show you two different implementations. One is like a toy implementation using NumPy, and this implementation, this is like an assignment from that class actually. So this will give you an idea of how they do it. And then there is in TensorFlow there is a better implementation for this, and we'll show you the results for both. So this is a GPU machine I created overnight. So I'll just show you. This one.
I'll add it to our GitHub. Thank you. So our next speaker, we're actually adding on a different speaker that is on the schedule for next. So if we get them plugged in really quickly, I'll give an introduction. Okay, so next up we have the future of mobility with Sarah Feldman. Please give her a round of applause.
Thank you. So I'm very excited to be here today. There's a lot happening in this space. It's definitely been expanding over the last couple of months, definitely the last couple of years. So thank you for having me. So let me go ahead and tell you guys a little bit about me. Why I'm up here. So I started actually primarily on the tech been able to pack GPUs, CPUs into vehicles, keep them cool enough where they can actually get us the results that we want as far as efficient, safe weather in regard to all these things. So these S-curves have aligned, and in the next couple of years, we're going to see a lot of different things happening with space. We already have transportation that's mass transportation happening that is autonomous, and we're going to start seeing this through ride-sharing platforms like Uber and Lyft, maybe even Tesla. So, who here is familiar with the last mile problem? Okay, quite a few. So for those of you who don't know, the last mile problem is a matter of solving, essentially taking BART, getting to a BART station, and not having to wait to get from BART to your house. That's kind of the summary of the last mile problem. Insert random municipal train transportation. So there is this problem where as you get closer to 1 mile, people's interest in walking drops off drastically. There have been a lot of studies across the U.S. and in other cities where, at a quarter mile, people are willing to go walk. At half a mile, it drops off by half. At a mile, very few people actually want to go walk unless they're in the immediate metropolitan area. Even still, it's very shaky. So because of that, you have this challenge that ride sharing is really starting to help with, and autonomous people continue to work on this problem. We're here at Excel.ai. AI is obviously a huge factor in what's happening with transportation right now. We have all sorts of things going on from Facebook ads to instances of this in transportation where vehicles may be assessing lane sharing or ride sharing, things like that, maybe designations for direction. So all of these are coming together. Another really important aspect of this, which I'm sure our elected officials, plural, possibly in the room, may be aware of, is regulation in the self-driving industry. There's a lot happening at the federal level, there's a lot happening at the local level. This is a place where, as tech folks, as I'm sure we've had a few here, it's really important to be engaged and to make sure that your local officials know that ride sharing, self-driving cars, fast transportation are things that you guys want, and shaping exactly what that looks like in the future. I'll talk a little bit more about that as well. So that brings us to a question that a lot of folks ask when they're looking at the future of transportation, and particularly self-driving cars. Which is going to happen first? We're going to have efficient, awesome self-driving cars that break the law, or is the law going to say, please have us, please welcome, the self-driving cars into our world. Tech isn't here yet, but we're still going to allow it. There's always this question, which will happen first? It's been really exciting, actually, to see the last year or so that there have been things coming in at the federal and local level, advocates going in cities, particularly in the Bay Area, to push this idea and to get the idea out that self-driving cars are a thing. They're coming. Mountain View's been very supportive. San Francisco's been very supportive. And you can just look across the board to see what's moving there. So, as I mentioned earlier, regulators are stepping up. This is really happening. The City of Palo Alto has provided APIs to their traffic signals. So, if you're a developer and you want to go test out your algorithm, you can find out through their open API what light is red, what light is green, what light is yellow, and work through that through real traffic signals. You can also look at City of Santa Clara. They recently had a RFP out for people to come in to work with them. We'll see what happens there. There is a lot happening in AV lanes, autonomous vehicle lanes, at a federal level as well. Seeing what will happen at a state level, what will be allowed. What's really interesting with autonomous vehicle lanes is this could really help substantially the safety issues and concerns a lot of people have with this mixed transportation potential of EVs and actual human drivers. Imagine human driver and a robot or an AI may act very differently as much as we try to act similar. So there have also been autonomous vehicle hub cities that have come out and been listed where development's being encouraged, regulations being potentially eased for that. And of course, the U.S. Department of Transportation had a course, they're looking at it from the aspect, from the sense of advancing self-driving local interstate. So, as I mentioned, a lot of cities have actually come forward and said we want to be a self-driving city. Figure out where those are, and there's a lot happening in Arizona right now. If you were to drive through Arizona at this second, you would see Waymo, Lyft, Cruise, Uber, all of these companies driving their autonomous vehicles just like you would see it now in San Francisco, even more so. It's pretty impressive. Tech is also stepping up. So this is what's also very interesting. Regulation is stepping up, and tech is stepping up. We have LiDAR, radar, AI, it's all happening. Perfect example, here is a self-driving vehicle. For those of you who don't know, the Tesla Model X has level 2 autonomous capability. Elon has definitely said over time that this is going to advance significantly, and I think he's made statements via Twitter saying that most likely in the next 5 years or so, they have the potential to be fully autonomous. And that's actually an incredible progress that's happening. The competitive landscape. I've been listing off a lot of companies. I'm sure some of them you guys have heard of, some of you haven't. These are kind of the big players. There's some here. There's some that I haven't listed. There's over 100 or so in the Bay Area alone. Mercedes not on that list. Honda's not on that list, but there are a lot of companies in this space right now. For anyone who is looking to get into this space, I encourage you to look at these companies, but also find out who other players are as well. This is the most you can hear first. We have Waymo, we have the Apple Car, potentially Uber, Lyft. Zoox is one that's really fascinating. They're in the area, and I've heard they have pretty incredible technology. Neo as well, and Cruise. So definitely keep an eye on these companies and see what they're up to. So as I mentioned earlier, there's kind of this concern that with autonomous vehicles and real human drivers, there can be just awful lag. Imagine you're walking through a city and just for fun you want to see if the autonomous car is going to stop when you stand in front of it. This is happening today. People in Mountain View, people across the world, are like, wow, this is a phenomenal thing. What if it'll stop? And this is happening everywhere. Now it's less so in the Bay Area, but I've talked to a lot of people who are from other countries, and they said, oh yeah, this is like a diamond, encrusted car running down the road. It's expensive, it's a novelty. People are, can do all sorts of things. And there's a lot of human behavior that has to be taken into account when you're coding for the AI of these vehicles as well. Keeping that in mind. But that being said, there is a lot of thought being put into whether or not we're going to end up in a utopian or a dystopian society when it comes to autonomous. And there's a lot of thought on the regulation side and on the tech side as to how to enforce a safe area for autonomous vehicles as well. And to that point, everyone thinks Yeah, so to my point earlier, some countries are already struggling with EVs. Norway's put in a lot of incentives to have electric vehicles, and they may not have the infrastructure. In fact, some of the regulators are saying, you know, maybe don't buy your electric vehicle unless you charge it at home. Now, this is what could be a game changer. Right now, people are not used to fueling their vehicles except out of burn. But if you plan to fuel your vehicle when you're plugging in your phone, you also go plug in your car, which is what I do. It starts to be more flexible. But the mindset and psychology behind it. So, how do you prepare yourself for this lecture? There's a lot happening and lots changing. We had a great talk earlier on TensorFlow. That is a huge game changer for AI. It's open source, which is mind-blowing. When I first learned about AI and ML, I couldn't make it myself. So study that, look into Udacity's self-driving course, study ML, study AI, and stay up to date on the regulations and news. So these are my suggestions. I hope you guys have enjoyed my talk. I'd like to thank you guys for being here.
Any questions?
And any questions as well. Any other questions? Thank you guys.
Okay, we're gonna have our next speaker come up. If you want to take a quick bathroom break, you're welcome to. And then her session will be pretty quick, and then we'll go on to lunch. Okay, everyone, so we want to introduce our next speaker. We have Kristen Henry. She'll be talking about data cleaning. Okay, and a little bit of data visualization. These are some very key components to working with data science and doing AI.
Okay. Hello. So does anybody here do data viz? Hands up. Okay. How much time do you spend prepping your data? Okay, who does not do data viz and still spends a lot of time prepping their data? doing any analytics whatsoever. Okay, if you use data viz, I'm just curious because when I do analytics, visualization is part of my exploratory process of doing analytics. So you'll see, I've combined this as a talk on both data prep and an example of how I might integrate a viz into my data prep process. I'm Kristen Henry. I'm a computer scientist. I work with data. I create data visualizations, and I also do generative art. So I've created a data cleaner in Python for myself that I use. I just found I was doing the same tasks over and over and over again, so I created a little Python script that I go back and I update and I use all the time. I do a lot of data prep. Sometimes I get really, really messy data. Data that makes you cry. Data that makes you scream. Data that just, you just go, why? Why? A lot of the fixes are repetitive. That's why having a script is great. And usually I can't do anything with the data until I've done something. Even something as simple as removing that first empty row in the CSV file. Even something just simple like that. I just want to run it through script quickly. And I don't want to open their Excel file. I don't want to do that. I just want to have the data. Created a tool for myself. It takes care of some of the drudgery. It's a working process. It's open source. I showed it to somebody once and I'm like, well, why don't you share that? I'm like, because it's not done. So I figured, well, I'll just release it. You can take it, build on top of it, and add any features you want. Eventually, it may become a package, but right now it's still a script. It's just pretty beginning step. I do have documentation on how to use it, so it's in my repo. If you want to grab it, these slides will be online if you don't have them already. So there's a lot of common data issues. Some are easy to fix, and some are a little more complicated. One that I see all the time are extra rows above the header even, not even just between the header and the data rows. That one will break anything if you put it through. Logos, business logos in a spreadsheet. Empty columns, empty rows. I don't understand why people put logos into spreadsheets. It's a very strange thing, but it's really common, happens all the time. A less easy fix is like I'm missing header names. Data formats are inconsistent. Multiple names for the same file or the same value, like it might be green street, S-T-R-E-E-T, or it might be green or it might be green stir, and the column is inconsistent. So I use a little tiny bit of natural language processing to recognize some of those patterns. And missing values in a column. One thing I see a lot is there'll be true false values, but they say, is the street, is the header name, and then it'll be yes, 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 and then all of these empty cells. So often I'll need to fill in those cells so that when I'm doing the processing later in my language, I don't have to program in error handling for the data. I want the data complete to my code. So this is a workshop, right? But it's only about 20, 30 minutes long, so we're not going to have time to do anything. What I'm going to do is I'm going to show you some examples, and then you can go play with it. Later, all the source code is on GitHub. Feel free to contact me if you have any questions. If I'm super busy and overbooked, it might take me a while. If I'm having insomnia, it might be instant. You never know. So the two tool sets that I use most of the time in my work are Python. I even create some viz in Python, but usually I'm creating visualizations that are meant for the web. So when I'm working for something on the web, it's D3. The example I chose is a set of that San Francisco OpenGov publishes, and it's a listing of the locations and the types of other data for all of the trees that are planted on streets within San Francisco city limits. So these are not the trees that are in yards or in parks, but they're actually registered with that lawn on where they are on the sidewalks in the city. It's kind of cool. About the data, it's already pretty clean, it's public, but it still needs a little bit of work. There are some missing values and there are some improbable values, which can be harder to find. So there's some interesting things in the data. There's a bunch of species names, there's locations, and for some reason, I thought, ooh, they have plum trees. That sounds interesting to track down. If you do afterwards, this is where the workshop is, well, all the source code. I have my Python code and my D3 code in there, so you can play with it. When I work, I usually edit my code in Sublime Text, and then I run it from command line. I prefer command line tools whenever I can. Anything that doesn't have to be opened up and shut down, that just slows me down. I just want to open a terminal real quickly, whether I'm on Linux or I'm on Windows. I can actually function as a programmer on Windows now. Pretty excited to get that working for me. I usually run a Python simple server. If you use Node, that's fine. So once you get the local host running, we're going to look at, I just created a simple bar chart counting up the numbers of different types of trees. And it looks like that. And already this is showing me some things about the data that I just didn't stand out to me when I was looking at this spreadsheet, and that is there's an awful lot of trees without names in the data set. The top bar is trees, colon. And then going down farther again, can you see my mouse? Yes. So there's this one that's totally blank. So it's not really anything particularly wrong with the data. It's just, it's not a value that I can trust or assign any meaning to. So I'm gonna just pull those out and strip them out. So in my cleaner, I just add command line, I want the phrase that I want to be skipped. Again, this is not super rigorous. I'm at the exploratory stage. Later on, if I'm working with this data set more formally, I will probably write a Python script that is unit tested. But right now, I just want to figure out what is going on in the data before I get down the road and I have to spend 10 hours fixing something that nobody saw. So these are the command lines for the commands for stripping out those phrases. Something to pay attention to, you must use double quotes. Single quotes will not work, or it's just a quote. So then I haven't changed my chart data much, but I have my new clean data set. Now I have a nice looking bar chart. Okay, cool. That was a simple cleaning task that could have taken me a really long time if I didn't just do this cleaning step first. What about mapping? We know where these trees are. At any opportunity I get to do math, I'm like, yes, please, I love mapping. But will the data cooperate? Sort of. We need to skip, just like we did with the values that had an incomplete or a blank name or a strange symbol for the name. We need to go through all of the records and see which one is missing positional data. Which way did somebody mess up on entering the data? Did they enter 00? Is it in the middle of the ocean? Is it outside of the city limits of San Francisco? Data is messy. Never, ever, ever trust your original data. You often have to go back and grind truth. So for this, I'm using JavaScript to filter it. And you'll see it's a bit slow. Let's see if it actually loads. Oh no, I have a screenshot of these slides. When you run it yourself, it could be a little slow too. Possibly very, very slow. So we open map 1. And now we have a map that's zoomable. You go in and out. And you can pan. This is is Mapbox tiles, and these are all of the trees in San Francisco that the city of San Francisco has a record for being planted in the sidewalks of the city. And it's very slow, even though I have a fast one. Now, notice I mentioned outside of the city we're in strange places. This is a zoomed out view. There shouldn't be any trees in the ocean off the coast of Canada. There should not be any trees off the coast of Africa. So if you want to do a really quick check to see if you're doing any mapping, just run your data through a simple map and just check the oceans. Trees are not supposed to be in the oceans. So we're filtering in the browser, and maybe I want to plot just one type of tree. And if we were a workshop, you would open this up, and then you get to see these are all the plum trees in San Francisco. You'll notice there are no trees in parks. That's because it's not that there's no trees in the parks, it's that this data set is only covering the trees in the streets. So when you're looking at data especially on a map, it's really important to remember what is the data set I'm looking at. Your mind will trick you. This is a data talk, but really from a viz perspective, especially with maps, you need to be very careful about the lies your eyes will tell you. Your brain will just assume that there are no trees where you don't have dots. See, it's a good idea to just like put a little gray, or just put a little, if we're in production, I'd probably put like a little square over here saying park. Or, because if you don't know the city, you might not know that that is going to be a park.
You have any Euclidean trees?
Yeah, but I didn't write the filter for that.
Okay.
I challenge you, write the filter for that and post it, and I want to see it. It's just really simple. Oh, that's the end. So I was trying to be really fast. So this piece, I actually put it up as an afterthought. I gave this workshop 6 months ago, and I was surprised how everybody loved this artwork. This is one of my very first pieces that I did of data art. Each dot represents the IP address of a spammer who is really annoying me. And the colors are the color map of the IP address itself. And then in the piece, this piece, when it runs, they kind of glob around like jellyfish. So this is how I work off my frustrations with spammers and do other kinds of crazy stuff. Why don't I, if I have a second, I try to show this up. Okay. Show up. So here's the street trees. I'm using leaflet and canvas because see how slow. Oh, wait a minute. I don't have Wi-Fi.
It's just open to the.
Oh no, I did. Look. Did you see how long that took to render?
Nice.
I'll do it again. Okay, okay, so now it's waiting. Oh no, it all worked out. I cached. Okay, let's try it. And these are palm trees. Mapbox is serving. That gives me an idea. So one thing to keep in mind when the tiles are reloading, your dots may not reposition in time. So you see that weird little trace thing I got there? Does that show it? So the trees are still where they are until they snap into place. Okay. And this is in the repo. Yeah. Oh no, that's the old one.
It's on our.
It's in there too, we're in October. Well, if you go to my repo, and you'll see there's workshop October and workshop July. The October one I've done some changes to, but I had a very short time. So we do have time for questions. You know that I got squeezed in. We have an extra 2 sessions in the time of 1 session today. So any questions?
So you're working with D3, right?
Yes.
It's notoriously painful. I'm
Really?
wondering, at least for me, I'm wondering, like, what you're mostly working with these math that you're using D3?
I'm using D3 Canvas and Leaflet. So Leaflet is a library that handles all of the map tile loadings. And I'm using Mapbox tiles underneath it. And I used so I used the grayscale Mapbox tiles because when you're mapping, you have to keep in mind what is the objective the user needs to accomplish. Are they trying to navigate where they are? Like with it, so are they using Google Maps? A Google map needs, or navigational map, has very different requirements than seeing data on top of a map. So with this map, I don't want the details of the map to distract from what the data is you're seeing. So, but you need enough of a map to give context. Otherwise, the dots are just strangely arranged and like, oh, that looks neat, but what does it mean? So with Leaflet, yay, Leaflet. Leaflet is amazing, and you can use any tile server that you want. And it's a really lightweight JavaScript library, and it does your point to lat long positions too. So I use D3 Canvas to draw because there's too many SVG elements here. There's too many dots. SVG, it'll just collapse. You can't really do more than 3,000 SVG elements, and that's pushing it. You had a question?
Yeah, somebody who has a lot of data that, you know, S is a dollar sign, or I've spent my life doing this peanuts, so, I mean, what would your advice be to me? Go to your site and write these or what's the,
How's your Python?
I don't have any yet, but we're not.
I would try using my script. Like if you know you have certain characters to replace, try. It won't work, so tell me, and I'll try to make it work.
Okay.
And we'll see. And then maybe we can get you to your Python skills to the point that you can implement the feature yourself. So this script, I'm the only one who uses it. So it works the way my brain works. It might not be the way your brain works. So you might think of things differently. So that's the weakness of this script. So although I have an awesome brain, it is unique, and not every user thinks the same. So the features, long story short, the features might not seem intuitive to you, but do try it.
Is there any sort of Python at this point you recommend?
Can you recommend an intro to Python? I mean, I learned it in grad school, so.
I actually have a program that I'm putting out and share with you to get people started from scratch on that. I'm new to that, so I put it in the journal.
And if you're not as familiar with command line, you might want to try an interactive Python shell, like IPython or Jupyter or something where you can see how that works. If you're not as comfortable with command line, it's a little friendlier.
Beginning your talk, you led with questions about analyzing separate worlds together. I'm curious, if you are aiming at analyzing data, what visualization techniques do you use as part of the process?
If it has a lat long, I try to put it on a map ASAP right away because that shows me a lot of inconsistencies. I'll usually start with a bar chart or a scatter plot, something really simple just to see if I've got some weird outliers that are really weird and not obvious. And people send me really weird data. People do very bad things in spreadsheets. It's Oh my God. Did that answer the question at all?
Yeah, it does. You're not working with less than long data. There's what is like your ability to more starts well, it makes sense features curious about your thought process.
It all starts with the data. Actually, before I get to Viz, I start crawling through the data with Python. I print out things, I test things, I look for clusters, I look for any kind of patterns I can find. I take like one look at the actual document, the spreadsheet or the JSON, or I try to get, if I'm lucky, there's a schema. If I'm lucky, but sometimes it's just a hot mess. And I'll try to print the headers, and I'm like, why is there no header? It's different every time. I do contract work, so I get data from a lot of different places, and I don't have the opportunity to train the data prep people into preparing the data that's really good, which is really common. When you think about it, you're trying to keep track of your company's records, and you're not thinking about it in terms of what is Kristen's code going to look like? How is she going to process this data? No, you put your logo in there because your company requires that every document be branded. You put extra rows in because you deleted something and you forgot to clear that row. Or, like, of course you only need to check mark the values that are in San Francisco. You don't want to go yes, no, yes, no. You're not being lazy, you're just maximizing the effect of your efforts. So, but we're on the receiving end of that. We can anticipate some of it, and we can cry, but we have to deal with it. We can help them be better, but really it's our job to clean it up. Sometimes. Yeah. Although the fun times are when they give me data and they say, we want to see what you can do with this. That actually can be really, really fun. Sometimes like the requirements are spec'd out by an exec who doesn't even know how to fill out a spreadsheet. So every project is different. Oh yeah, it all starts with the data. I start with command line, trace through things, write a little Python script, see what I can get. Even in the browser, I usually don't actually plot to the screen until after I've done a bunch of traces through the data to see if I've got what I think I've got. Even my own data isn't perfect. Any question? A lot of data that I get isn't even ready for pandas. And then by that time, I might as well just write 3 lines of code to fix that. And a lot of the stuff I do is exploratory, proof of concept work, so I'm not doing into production as much. Once it was moving into production, probably with pandas, but you have to make sure that everything is ready. Most of it breaks. That's why my tool is really simple. I don't have a lot of it's just like I don't want to open the file, I don't want to close the file, I don't want to add pandas. It's like they're ringing the bell for me to leave.
We give her a round of applause, please. We're going to take a break for lunch. We originally scheduled an hour. We're going to cut it to 45 minutes. That should still be enough time. Just do some more interactive activities. So just letting you know in advance. But please go ahead and take lunch. There's food in the back thanks to Google Launchpad. So see you guys in a few.